So let's say we want to multiply some numbers. Two complex numbers written in exponential form, kind of like we just did. And we're just going to sort of develop and really, I guess, formalize the process we kind of just went through in that problem we worked out. So I'm being, these are arbitrary numbers. I'm not being specific. So they have their own modulus values, R1 and R2, and they have their own directions, theta 1 and theta 2. So we can multiply in any order we like. So we can jumble up the order, R1, R2, e to the j theta 1 times e to the j theta 2. And then we can multiply these guys. Right, using our rules of exponents, because it's the same base. We can just add the exponents. So I have j theta 1 plus j theta 2. And then a tiny bit of algebra, one more step, just to looking at that the exponent. They both have a factor of j, so we could just factor it out. J times theta 1 plus theta 2. So here is their product. And basically, if we translate this, now if we want to write it in like the trigonometric form, we could see exactly why we get the product above, right? If we were to start out with this, it is not entirely obvious what we should get here. But because we know that the trigonometric form has like this one-to-one correspondence with how we write it in the exponential form, now we know how to multiply these two numbers. We know exactly what we're going to get. What should the result be when we multiply these two together? In other words, let's observe that this number here to begin with is R1 e to the j theta 1, and that this number here is R2 e to the j theta 2, right? It's just whether we write it in the trigonometric form or the exponential form. We just worked out how we multiply these two, and we saw what we should get. So writing out the result, we can jump straight to the result here. This result should end up being R1, R2. I'm grabbing this straight from right here. And then our new angle is theta 1 plus theta 2. So I open up the set of parentheses and I have cosine of theta 1 plus theta 2 plus j sine theta 1 plus theta 2. The exponential form, that particular type of polar form really gets us a lot of insight into how we do arithmetic with these complex numbers. Because I don't know, I mean, at least to me, it's not really obvious that when I multiply numbers in this form, that this is what the result should be. But I know it's that case because we worked it out in the exponential form. So, the punchline here is, of course, if we're going to multiply two complex numbers that are in polar form, all we have to do is we get the modulus by multiplying the two moduli. We get the direction by adding the two angles. And then we want to make sure that the angle that we give is between 0 and 360 or 0 and 2 pi if in radians. Just like with vectors, right? We want to make sure we have a standard position angle that just accounts for one go around the circle. So here's a quick product to find. It'll be very little work involved here. See how much space I allowed for this problem. It'll be quick. All we have to do, multiply the two moduli and add the angles. So we have 6 at an angle of 125. There's the answer in polar form. I'm doing a quick check. Positive 125 degrees. That is a standard position angle between 0 and 360. So that's perfect. And unless they ask me to write it in some other form, I can stop right there. That's it. That's even easier than foiling two complex numbers. All right, let's do some division. Let's take those two arbitrarily chosen complex numbers right, with their arbitrary moduli and angles. And let's now divide. Now we can split up fractions over a product, right? In other words, I could take that fraction and write it as R1 over R2 times e to the j theta 1 over e to the j theta 2. Those are definitely equal to each other, right? That's how to go from the right side to the left side is fairly straightforward. So we're just splitting this up. Now, what do we do with that? How can we simplify that fraction? Yeah, so we still have the same base, which means we can subtract the exponents. So we have e to the j theta 1 minus j theta 2. And just like we did on the previous page with multiplication, both those terms in the exponent have a j, so we could factor it out. So there's our quotient, written in a polar form. Right, the new modulus is just the quotient of the two moduli, and the new angle seems to just be the difference of the angles. I have the top angle minus the bottom angle. And this all makes sort of perfect algebraic sense when we can work it out in the exponential polar form. So in the trigonometric polar form, we're just going to grab the work that we already did. We know our new modulus is just R1 over R2, and then our new angle is the difference here. So open up a set of parentheses, cosine theta 1 minus theta 2 plus j sine theta 1 minus theta 2. When we're dividing, we need only divide the two moduli and subtract the angles. And then make sure at the end, if we're writing our answer in polar form, that angle is a standard position angle between 0 and 360. So let's say I wanted to find the quotient here. Well, using the rule, there's going to be, not a whole lot of work required here. My new modulus is 2/3, and then I've got cosine of my new angle, 55 minus 70. And 55 minus 70 is negative 15. And the only thing left to do to finish this up is just to realize, oh, well, in this case we got a negative angle when we subtracted, so we got to fix that. And if you get a negative angle, just add 360, or, subtract 15 from 360. And that gives us 345. So there's our angle. And of course, as a lot of us might get in this habit, it's totally okay right at the get-go to adopt this sort of notation. I was just using the cosine j sine notation because that's what we started with, but you could work the whole problem out kind of with that shorthand notation. Does anybody have any questions? Okay.
Do you mind scrolling back up?
Not at all. Like this to this place?
Yes.
Okay. Mm-hmm. So in this problem, they want us to multiply the complex numbers, which we could do in rectangular form. We already know how to FOIL stuff out, but they're asking us to do it by first converting H to polar form. So we'll get a little practice converting to polar form. So let's work with 2 plus 3j first, right? So we got two sort of little miniature problems contained within this one. 2 plus 3j is in the first quadrant. So our value of r is the square root of 2 squared plus 3 squared. So we get 5. No. 4 plus 9, root 13. And how do we get the direction?
Arctan y over x.
Mm-hmm. Arctan of 3 over 2. And it's first quadrant, so we don't have to make any adjustments to this. (56.3 degrees) if we're in degree mode. It is perfectly acceptable to work through the whole thing in radian mode and just have your direction in radians. So that means that 2 plus 3j is equal to root 13 at an angle of 53.6 degrees. So now we'll do the 1 minus j. And 1 minus j, well, this is over in quadrant 4. So r is the square root of 1 squared plus negative 1 squared. Sometimes people make the mistake when we're finding polar form here, especially when that coefficient on j is just a 1 or a negative 1. They just really want to put the j in the radical, but it's just the coefficient, right? So it's 1 squared plus the square of negative 1. J does not go anywhere in that radical when we're finding r. And so we just get the square root of 2. Now my calculator is in degree mode right now, right? That's why I got 53.6 degrees before. And because this is in...
Yeah, about that. Did you actually get 53.6 or did you get 50?
I got 56.3. Yep. Funny you should ask. Thank you.
On the top too. When he says 2 plus 3.
Oh, yep. 50. There we go. Thank you. So I'm in degree mode. That's still true. And so in this number is in quadrant 4. So what do we need to do to get that angle?
360
Minus 3.
Yeah.
360 minus.
Yep. So 360 minus the arctan of, and I just put in positives here. So arctan of 1, basically. That gives us 345, I think. No, 315. I should probably just do it now. I don't trust myself. 315. Okay. So we have these pieces done. So now 2 plus 3j multiplied by 1 minus j is equal to the product, root 13, 56.3 degrees, times root 2 at an angle of 315 degrees. So that means if we're going to multiply, we just multiply the two modulus values. Oops, root 13 times root 2. And what do we do to the angles? Add them together. So our new modulus, we're multiplying two radicals, so we can combine them under one radical. So we have root 26 at an angle of 315 plus 56.3 is 371.3 degrees. This is sort of in polar form, but there's one thing we need to fix. Yeah, well, it doesn't have to be in radians, but it's more than 360. Yeah. So our last step is just to subtract 360. If you get a result that's bigger than 360, just subtract 360 and you'll get your angle that you need. There are some actually coming up. We'll see some instances where we might get an angle that's really bigger than 360. So just keep subtracting 360 until you get something that's between 0 and 360. If you get something that's negative, just add 360 until you get to your first angle that's between 0 and 360. So we have root 26 at an angle of 11.3 degrees. You can check this and convince yourself that this gives us an accurate result. You could find the rectangular form using the cosine and sine functions here, right? The way we convert from polar to rectangular. And what you get should be equal to, at least very, very close to, because we did have to do some rounding with the angle, what you would get if you FOILed out the product in the rectangular form. So let's do another one. We're going to divide now by using the polar form for each. These are the same numbers we just did, so we don't have to find the polar forms over again. We can just reuse the ones we did before. So we got root 13 at an angle of 56.3 divided by root 2 at an angle of 315. So now we're going to divide root 13 over root 2. And what do we do with the angles? Subtract. While we're here, we're going to do the subtraction and maybe have to fix that angle, but may as well rationalize this denominator. So we got root 26 over 2 at an angle of, what does this give us? Negative 258.7. So we got a negative angle, which means there's only one thing left for us to do to fix this, and that is add 360. .3. And again, if you found the rectangle, if you converted this to a rectangular form, this polar form to a rectangular form using the cosine and sine functions, you will get the same or very, very close, right? Because we had to round to get that angle to what we would get if we divided those using, like, by multiplying by the conjugate on the top and the bottom, like that whole thing. So the polar form can be pretty convenient for multiplying and dividing complex numbers. It should be noted that if you need to add and subtract complex numbers, you got to do it using the rectangular form. So even if you were given a problem and they were like, add these complex numbers, and they gave you the numbers in polar form, then your first step should be, let's put them in rectangular form and add the real parts and then add the imaginary parts. Okay. Stay with me. This is starting to get fun now. All right, so powers and roots are things this is when things really kind of start to get fun. There's this famous result, call it de Moivre's theorem, that tells us how we can raise a complex number to a power if it's in polar form. And it is exactly what we think we ought to be able to do if we write it in the exponential form, right? Like if I'm raising a number to a power in this exponential form, well, we know we get to distribute a power over a product. So I have r to the n. And if I take e to the j theta and I raise that to the n power, well, we multiply the exponent. So it's not so surprising that we have n theta as our angle. And over on the other side, it's just written in that trigonometric form. So raising a complex number to a power means we're making it, is essentially telling us how we change the modulus, right? That sort of makes sense that we just raise the modulus to the power. but also that we're like kind of rotating it. There's like this sort of geometric interpretation of what it means to take a complex number and raise it to a power. So let's say we want to find the value 2 plus 3j cubed. It says evaluate and express the result in rectangular form. Well, it'll probably be a little easier if we just write it in rectangular form, in polar form to begin with, especially since we already found the polar form in the previous problem. So 2 plus 3j, this is root 13 at an angle of 56.3 degrees, and we're cubing it. So de Moivre's theorem says we're going to take the root 13 and cube it, and then multiply the angle by 3. If we cube root 13, we should get 13 root 13, right? Because we have 3 of them, so 2 of those root 13s become a 13. 56.3 times 3 is 168.9. So there's our polar form. We want it in rectangular form, so let's do that. So we're starting with 13 root 13. I'm going to actually use the trig function, the trig form, to write it here. So cosine 168.9 plus j sine 168.9. And we distribute. We get negative 45.995. So pretty darn close to negative 46. And 9.024 plus 9.024j. So there's our rectangular form. We had to do some rounding when we worked with the, when we found the angle, when we initially, were using the arctan function to get that angle. So I'm willing to bet that if you FOILed out that product, 2 plus 3j cubed, right, like use FOIL in algebra, you'd probably get exactly like negative 46 plus 9j. How'd you like that?
Oodles of fun.
Oodles of fun? I'm glad to hear you say that. Because we're going to do the most awesome thing right now. So finding roots and powers are really the same thing. Right? The square root is a 1/2 power. The cube root is a 1/3 power. We've been working with that for a while now. So if I want to find roots of a complex number, it's the same as raising it to a power. We can use de Moivre's theorem to help us with that. Now, here's an awesome fact in mathematics that says we're already used to the fact. Like, if you just think about regular positive numbers, we're used to the fact that every positive number has 2 square roots, right? A positive and a negative one. If you allow yourself to use complex numbers, the negative numbers also have 2 square roots. They're just imaginary. But we can go even further and say every complex number, not just every real number, but every complex number has precisely n nth roots. So there are 3 cube roots of every number. There are 17 17th roots of every number. There are 2 square roots of every number. And we can use de Moivre's theorem to help us with that. What we do is, there's a certain sort of symmetry and geometry to these roots. De Moivre's theorem will help us find what we call the principal root. That just means the first root. The other roots that exist, like if I'm finding the cube roots, right, I'll find the principal cube root. The other two will be the same distance from 0. So they'll have the same modulus, but they'll just be equally spaced around like a circle. So if you were to like kind of plot these roots, they're almost like spokes on a wheel. So we're gonna start out. We're gonna do an example. We want to find the cube roots of j. So the first thing we need to do is write the number in polar form. So j is equal to, well, it has a modulus of 1. What's its angle? So j is right up here, right? 90, yeah. Now what we're going to do is say, okay, I want to find the principal root. That's what we're going to set out to do first. We want the cube root of j, which means we're going to find 1 at 90 degrees raised to the 1/3 power. We can use de Moivre to help us with this. De Moivre tells us that this is 1 to the 1/3 at an angle of 1/3 times 90 degrees, or 1 at an angle of 30 degrees. We didn't have to work very hard to get the polar form of j because it was just straight up, the angle is pretty easy and everything. But usually this process of finding the polar form of the number and then getting that principal root, that's usually where you do the bulk of your work. The other two roots now are going to be equally spaced. They're going to have the same modulus, so they'll also have a modulus of 1. But they'll be equally spaced around a circle. So, the way we get the other roots is we simply add 360 over 3. We're adding 360 over 3 because there are cube roots. If I were finding like the 5th roots, I'd add 360 over 5. If I were finding the 7th roots, I'd add 360 over 7. So we add that to the angle, which means we're adding 120 degrees to the angle. So our second root is, we have, let's see, a modulus 1, and then 30 plus 120 is 150. And our third cube root, because we know there are 3 of them, I'm just going to add 120 again. So I have 150 plus 120. And that's 270. So in polar form, this is what they are. These are the 3 cube roots. And by the way, if I just sort of was having so much fun and lost track of where I was, and I was like, okay, now let's find the 4th cube root, I'd add 120 again, but that would bring me back to the original first cube root. So it wouldn't produce any new numbers. If we could then, if we were asked to get the numbers, if we wanted these roots in rectangular form, we know how to get from polar to rectangular form. It's not too hard. But here are the numbers in the polar form. And now if we were to plot these, our first one is, let's see. Let me do it this way. So this is a circle of radius 1. I picked radius 1 because that's the modulus of our first root. And basically what they are is they're all equally spaced. So our first one had an angle of 30 degrees. Our second one had an angle of 150 degrees. And our third one had an angle of 270 degrees. So these are our cube roots. It's basically like a flux capacitor here. Equally spaced. If we were finding like the fifth roots, there would be 5 of them, sort of equally spaced, all around a circle of the same radius. So one result of the fact that every number has nth roots, one sort of result of that is a theorem we call the fundamental theorem of algebra. So given its name, you can imagine it's sort of a weighty result. But it just says any polynomial equation of degree n will have n solutions as long as you allow yourself to take solutions from the complex numbers. So, for example, if we want to find all roots of the equation, and I think we've seen this word used in this sense before on the homeworks, a root of an equation just means a solution. So if we want to find all roots of the equation, x to the 6 minus 64 equals 0, the first thing I do is I look at that and I say, well, there's going to be 6 of them. So I know that I'm looking for 6 answers. And one of the first things I would do here is just rearrange this equation. This means that x to the 6th is equal to 64. And when I write it that way, if I want to figure out what x is, I can see really what I want is to find the 6 sixth roots of 64. So 64 is a positive real number, which means its angle, when we write this in polar form, it has a modulus of 64, and its angle is 0 degrees because positive and real. So first we find the principal root. We want the 6th root of this number. So we want 64 at an angle of 0 degrees to the 1/6 power. Demarov tells me all I have to do is take 64 to the 1/6 power, multiply the angle by 1/6. 64 to the 1/6 power is 2. So 2 at an angle of 0 degrees. That's the principal root. It's also just equal to 2, right? And that's a positive real number. That is the solution we would find normally, right? If we were just looking for the 6th root of 64, when we just want to find the 6th root, like on our calculator. And we would probably at that point stop. And maybe we'd look for one more and say, well, there's probably a negative one as well because it's an even root. But we know that there are going to be 5 more, so we need to find them. So let's get the second root. We know it's going to have the same modulus of 2. How do we get the angle? Say that again? 360 over 6. Like, so what we do is we take the angle we had from our previous root, in this case 0 degrees, and we add 360 divided by 6. You take the whole circle and you divide it up by the number of roots. That's how far apart those roots are spaced around the circle of this, in this case, the circle of radius 2. Like before, when we were, when we took 360 and divided by 3, we got 120. That tells us like how far angle-wise these guys are apart. Each of these is 120 degrees. So that's 60 degrees. So that 60 degrees is what we're going to add each time we want to get a new root. So we get 2 at an angle of 60 degrees. And we can find the, why don't we go ahead and find the rectangular form. So we have 2 cosine 60 plus 2 sine 60 degrees times j. 60 is kind of one of those convenient values. So cosine of 60 is a half, so multiply that by 2 and we get 1. Sine of 60 is root 3 over 2, so we have root 3. So there's our second root in both polar and rectangular form. Let's get our third root. What do we do to get our third root?
Add 61.
Yeah, add 60 again. They all have the same modulus. You just keep adding 60. So I take the 60 degrees, I add another 60, and we have 2 at 120. And so there it is in polar form. We can get the rectangular form. Cosine of 120 is negative a half, so this is minus 1, and that'd be plus root 3 times j. So we have 3 roots. There's only 3 more to go, you guys. So I take my 120 degrees, I add another 60. Which is 180. What is the rectangular form for this number, magnitude 2 at an angle of 180? You can draw it, and you probably get there faster. Well, cosine of 180 is negative 1. Yep. What's the magnitude? No. Our magnitude is 2 in this problem. Right, our principal root had a magnitude of 2, and all of our subsequent roots inherit that. So this result is negative 2. Our fifth root, add 60 again, so 180 plus 60 is 240. Cosine of 240 is negative a half, and sine is negative root 3 over 2. So we have negative a half times 2 is negative 1, and this will be a minus root 3 times j. One more to go. Add 60 one more time. Oh, whoops, 300. 2 cosine of 300 plus 2 sine of 300 times j. Cosine of 300 is positive 1/2 and sine is negative root 3 over 2. So that means this will be a positive 1 minus root 3 times j. Those are our sixth roots of 64. How's that? Get excited, you guys. Like, that's cool. No? Okay. I'm trying.